Hello, I'm Athena Bahrami Ahmadi, a PhD student at the University of Alberta, working under supervision of Dr. Rick Chalternik. In this presentation, I'll be talking about our numerical research on comprehending the impacts of anisotropy and size dependency on the mechanical behavior of sandstone using the X-ray microscopic data. Rock's mechanical behavior is influenced by their diverse composition and microstructures. This diversity comes from the variations in mineral content, grain size, and shape, and along with the factors like porosity and microfissures. When external stress is applied, these elements can impact how easily rocks fracture or deform. As Griffith and his colleagues have shown, the arrangement and angle of these features related to the applied force are important factors in predicting how rocks will behave under stress. The figure on the right shows a sample of the Montney Formation gas shell. This illustration highlights unique characteristics of shell, particularly its anisotropy and internal structure. Our main goal is to forecast rock mechanical properties by using two systems designed and built at the Reservoir Geomechanics Research Group here at the University of Alberta, the mini-triaxial cell and sudden impact load cell systems. These systems utilize samples with diameters of 10 millimeter or less to analyze mechanical properties of rocks. By doing so, we can examine how anisotropy and sample size can influence the outcomes of our tests. On the right side of the screen, we have CAD designs of both systems. What's unique about these systems, aside from their small sample sizes, is that they are equipped with high-speed cameras. This addition allows us to employ digital image correlation methods, which can be used as an additional tool for a deeper understanding of the mechanical behavior of rocks. The image at the bottom shows the size of the samples used in mini-triaxial system. We have successfully tested samples from the highly fractured Duvernay Formation in reservoir conditions of 20 megapascals using the mini-triaxial system. As part of our methodology, we used X-ray microscopic data to examine a sandstone sample using the deep learning segmentation module of ORS Dragonfly software. Through this analysis, we were able to identify both the voids and glauconite structures within the sample. These findings were then used as inputs for our numerical modeling, which we use the Itasca PFC 3D software for. The model is built within the discrete element method framework and utilizes a bonded particle model. Unfortunately, due to the computational limitations, we had to upscale the original structures that we obtained from the XRM data by downsampling the voxel size. And then we conducted simulations using this modified pseudo-real rock geometry, taking into account both porosity and anisotropy within the structure. In this slide, we are showcasing the results of our numerical simulations with a particular focus on the anisotropy within the sample. This anisotropy arises from the presence of the glauconite inclusions within the sandstone. As depicted, we have observed variations in the sample's highest compressive strength based on the angle of anisotropy in relation to the loading direction. As shown, the highest compressive strength is achieved when the anisotropy angle is set at 30 degrees. On the other hand, in the lower row of the figure, you can see how shear and tensile failures localize within the sample. These visualizations demonstrate that shear failures tend to occur in highly stressed regions of the sample. We also explored the size dependency of rock mechanical behavior in our study. To investigate this, we divided a 20 millimeter tall sample into subsamples. Samples 1 to 3 were taken from the lower half, while samples 4 to 6 were taken from the upper half of the original sample. On the right-hand side of the screen, you can see the results of the compressive test of seven samples. We have also provided visualizations next to each sample, where red represents shear failure and blue represents tensile failures. Additionally, we have included a chart that illustrates the relationship between the glauconite content, porosity, and the maximum compressive strength of the sample. In conclusion, our research has highlighted the impacts of inclusion density and orientation related to the loading direction on the observed stress strain curve outcomes. Specifically, when glauconite, with its higher density compared to the surrounding matrix, aligns with parallel to the loading direction, it acts as a stress concentration layer, leading to early specimen failure at reduced strains. However, when the inclusion is oriented at a 30-degree angle, mirroring the anticipated shear plane angle, the specimen exhibits greater deformation tolerance before failure. Additionally, the findings from our study reveal key insights on failure modes. Tensile failures tend to occur more frequently around the sample edges, while shear failures predominantly centralize when contact forces peak. The location of bond disruption is notably influenced by the inclusion's position and the density. Stress at failure is a complex interplay of various factors, including the sample's porosity, glauconite content, and the intrinsic properties of the matrix. These parameters don't exhibit a linear correlation, often offsetting one another. Also, we observed that the specimen's peak stress at failure is lower than its subsamples, despite similar glauconite and porosity values. This study shows the importance of comprehending the relationship between sample size and mechanical behavior, and we plan to delve into detailed statistical analysis in our subsequent research. Finally, we extend our heartfelt gratitude to Nathan Daisman, Jacob Brandel, Emmanuel Mwangi, Bhavesh Morker, and Thomas Barton for their invaluable assistance to the design and construction of the mini-triaxial and sudden impact load cell apparatus. Their expertise and unwavering dedication is playing an important role in the success of this project. Thank you very much for your attention.